Just 1 minute, please. I'll increase this thing so that we can see better. Okay. Okay. So what we will do by the frame structure, I mean the time domain, OFDM time domain structure. So we'll start with this document 38211. I'm going to open the 38211 document and then we will start going through that. Okay. So this is the main, as I was telling last time, this is the main physical layer specification. Okay, this is what talks about the physical layer channels and modulation. Okay. So as usual, this is scope. It says the physical channel and signals. We understand now what are physical channels and what are signals. Now, physical channels are something that come from the higher layers. Signals are something that are generated. Reference signals are something that are generated inside the physical layer. Okay. There are multiple symbols and other things. So if you don't understand any symbol, you can come here and look at the symbols thing, and it will be here. Okay. So that's something that helped me quite a bit sometimes. Also, there are abbreviations. Okay. So let's start at this point. This is where this whole this is where the whole thing starts. Okay. So essentially, first thing, let's just take a little bit of time and read 4.11. Okay, and then I will explain. Okay. Throughout the specification, until unless otherwise noted, the size of various fields in the time domain is expressed in time units of TC, where TC is equal to 1 by delta F max into NF, where delta F max is 480 kilohertz and NF is equal to 4096. Okay. So what this means? Okay, so time domain, essentially in time domain, we have to define samples and sampling time. Okay, we have to talk about some time in the time domain. Okay, so this is the fundamental unit of time in 5GNR. That's called TC. Okay, so what is actually TC? Let's just let me just write it up and then you'll understand it better. TC is equal to 1 by 4096 into 480 kilohertz. Okay, so if you think about this, if this is your N and this is your subcarrier spacing, okay, this is your FFT size N and this is your subcarrier spacing. TC is nothing but TC is nothing but sampling rate of an OFDM symbol with 4096 subcarriers and 480 kilohertz subcarrier space. Okay, so essentially, effectively, this says that this is the highest. I mean, this is so. If you think about this, what is the bandwidth corresponding?
This is the sampling time, not the sampling rate.
This is sampling time, sir.
Yeah, sampling time. Yes.
Yeah, sampling time. So the maximum, the bandwidth corresponding to will be 4096 into 480 kilohertz. How much is this? 4096 into 480. This is 1966080 into 10 power 3. This is 1.96608 gigahertz. Okay. So this is 19968. So this is a maximum data rate, that maximum bandwidth that the 5GNR supports. Okay. Is this clear? Okay. So it says that this is a fundamental unit of TC. Suppose I give you a problem. Suppose I'm using only 4096 subcarriers and I'm using 30 kilohertz subcarrier spacing. Okay. So my sampling duration will be 1 by this. This will be my sampling duration. Now, this is what we learned. This is a band in OFDM. This is the bandwidth, and 1 by bandwidth will be my sampling time. So what is the relation of this time with TC? Can anyone tell me? So this is, if I call this as T sample, T sample. What's the relation between T sample and TC?
Can you repeat again, sir? What did you say?
So TC is this. TC is defined as this. Okay. So suppose I have an OFDM symbol. I'm doing 30 kilohertz subcarrier spacing with 4096 subcarrier. This will be my sampling right now.
Sir, your mouse pointer is not visible, sir.
Oh, sorry. No, I'm writing something. I did not. Okay. So really sorry. Okay. So TC, this is TC. This was TC. This is what we defined as TC. This was what we call as TC was defined like this. Okay. So what I'm saying now is, suppose you have 4096 subcarriers and you are using 30 kilohertz subcarrier spacing. Okay.
16.
Sorry.
Ratio will be the 16, 1/6.
60. Yeah, 60. Exactly. So T sampling would be equal to what do you say? TC into 16. Yes. So the T sample and TC is TC into 16. Okay. So this is how they express all the time domain things in terms of TC. Okay. So TC is the fundamental unit of time in 5GNR. Okay. Let's get back to this. Okay. Now let's see this. They also define something called TS. Okay. TS, if you look at TS is nothing but 15 kilohertz subcarrier spacing and 2048 subcarriers. This is nothing but LTE. In LTE, what do we use? LTE we use 15 kilohertz subcarrier spacing and NREF is equal to 2048. 2048 into 15 is how much? 2048 into 15. Okay. So this corresponds to the 20 meg. I mean, I'll tell you how this corresponds to 20 megahertz later. But this corresponds to LTE, 15 kilohertz subcarrier spacing. And they define this small kappa, K, as TS by TC, which is 64. Okay. This is fine. So you should always remember TC. TC always corresponds to 4096 subcarriers and 480 kilohertz, which is the highest subcarrier spacing in 5GNR. Okay. So theoretically, 5GNR can support up to 1.9 gigahertz. I mean, no. I'll take that. I'll take it back, but we will just keep TC as it is. Okay. Any questions on this? You understood TC?
So the sampling rate is always highest in 5G, or corresponding to different numerology, we use different sampling rate as gets calculated?
Yes, we use different sampling rates, but different numerology, we use different sampling rates, and that will be expressed in terms of TC always.
So that means when we use 15 kilohertz subcarrier spacing, the sampling rate would be equal to the sampling rate which is used in LTE.
In LTE, yeah, 15 kilohertz depending upon the bandwidth. I'll come to that, sir. I'll explain that. Depends on the bandwidth. I just gave an example. Now, if you use 30 kilohertz subcarrier spacing and you use 4.
For the maximum bandwidth, but because NREF has to be taken accordingly, right?
Yes. So this, so these are two constants that are defined. These are constants. These are two constants. Everything will be expressed in terms of TC and TS. Okay. Okay. It will become clear once we go into a little bit more. Okay. So the next thing that says is, multiple OFDM numerologies are supported in 4.21. Okay, where mu and the cyclic prefix for a bandwidth part. So, okay, so essentially, what are the different subcarrier spacings that are supported? Delta F, 15 kilohertz, 30 kilohertz, 60 kilohertz, 120, and 240. Okay, so how they mention this is they map. If you see this, all these values can be written as 2 power mu into 15. If mu is equal to 0, you get 15. Mu is equal to 1. 2 power 1 into 15, which is 30. 2 power 2 into 15, which is 60, 2 power 3 into 15, 120, 2 power 4 into 15, 280, 240. Okay. So generally they specify mu. Mu corresponds to the different subcarrier spacing. Mu is equal to 0 is 15 kilohertz, mu equal to 1 is 30 kilohertz, and so on and so forth. Okay. So you see a lot of mu in the entire specification. So each mu corresponds to specific subcarrier spacing. They always specify in terms of subcarrier spacing. Fine. Is this clear?
So the maximum subcarrier spacing defined in this table is 240, whereas for calculating TC we have taken 480. So 480 is something which will come in future.
In future, sir. Yes, this release 15 only supports up to 240. Okay, 480 is already there. 17 and other things to do some small parts.
we also heard about numerology -1, where 7.5 kilohertz subcarrier spacing can be used mainly for IoTs.
IoT, yeah. There is, that is true, but we will not go into that right now, sir. Okay, what you heard is true. Okay, but that's there in the later releases. If you just stick to release 15, this is what we have. Release 15 and 16 also, this is the same thing. There's a 480 also, but 480 is used only when some very specific circumstances. Okay. So one more thing that is there is a cyclic prefix. The cyclic prefix normal, extended. So 60 kilohertz has something called extended cyclic prefix. Okay, so we also learn cyclic prefix is mainly determined by the, the delay spread of the channel. And when you have larger cells, you have larger delay spread. So, okay, so this generally these extended cyclic prefixes are used for large, very large cells. Okay, but in this course, we will not worry about extended cyclic prefix. Okay, we will understand the normal cyclic prefix, and once you understand normal cyclic prefix, changing to extended is very straightforward. Okay, otherwise it will confuse us quite a bit. Fine. So in this course, we'll just focus on the normal cyclic prefix, and we'll try to master that. Let me show you some slides. I'm going to. Okay. So now, how do we read this spec? Okay. So when we read this spec, it says where mu and the cyclic prefix for a particular bandwidth part, I didn't talk about bandwidth part, I'll talk about it later, are obtained from the higher layer parameters, subcarrier spacing and cyclic prefix respectively. Okay. So how does the base station tell the UV what is the subcarrier spacing, what is the cyclic prefix? Okay. So this is a slide. I made. So essentially, multiple subcarrier spacings are allowed in 5G and R, unlike LTE, which has only 15 kilohertz subcarrier spacing. Okay. Forget about the yellow thing. There are some things that I write. We can understand that later. So one thing that we understood is as the subcarrier spacing increases, the size of the time length of the OFDM symbol is 1 by delta F. Okay, that's what we learn. Yes. So if you have 240 kilohertz subcarrier spacing, you have the lowest latency, whereas 15 kilohertz gives you the highest latency. Okay, that's one thing. And one other thing that we have also looked at is because of frequency offset, the maximum amount of frequency offset that you can tolerate is a percentage of your subcarrier spacing, maybe 1% of your subcarrier spacing. So if you have a larger subcarrier spacing, you can tolerate higher frequency offset. It turns out that the millimeter wave systems have higher, CFOs. Okay? Higher CFO, because the frequency is high, the CFO also will generally be high. So generally what happens is the higher subcarrier spacings are generally used in FR2 and the lower subcarrier spacings are generally used in FR1. Okay, so you saw now I put this, I distinguished them. So FR1 uses 15 kilohertz and 30 kilohertz and 60 kilohertz, whereas FR2 uses 60, 120 and 240. Okay. The main reason is one is the resilience to frequency. So I think there's a lot more frequency offset errors in FR2 compared to FR1. So they also have to, to make it more resilient to this thing, you also require a larger, subcarrier spacing. That time there's a notion of something called phase noise, which is again very related to CFO.
So if we use, say, 15 kilohertz subcarrier spacing in a gigahertz frequency band, high frequency band, so what is the problem which we'll get?
So if you use 15 kilohertz in millimeter wave system, suppose 26 gigahertz, what happens is, see, there's something called phase noise. I haven't talked about this. So phase noise is how your oscillator, in addition to having delta F, will also have some random movements. It's called the phase noise. That phase noise actually plays a very critical role in finally the performance of OFDM systems. Okay, so essentially phase noise is very similar to delta F, but delta F is not changing over time, whereas phase noise changes over time. It's like delta F changing over time. Okay, in terms of the phase noise is very large in millimeter wave systems. So if you have lower subcarrier spacings, we saw what we saw was what did we see? We saw that if you have lower subcarrier spacing, then your frequency has to be much more tighter. Delta should be lower. Okay, so that is the reason why lower subcarrier spacings are not used in FR2 because of frequency offsets and phase noise.
Okay, so that's a phase noise which is the problem. And what is the reverse reason for the reverse? Lower frequency and higher carrier spacing?
Lower frequency and lower carrier.
Higher subcarrier spacing, yeah.
Why don't we use higher subcarrier spacing in? So it turns out if you have higher subcarrier spacing, this is a problem I'm going to give you in your assignment this time. Your CP length, how much you use some CP. Okay, the amount of CP that you use depends on your what does it depend on? It depends on your delay spread. As a fraction of time, how much your CP length is depends on delta F again. So it turns out the higher subcarrier spacing they use, then the larger amount of wastage in terms of resources, okay, in terms of overheads. So this is a trade-off that you do. I'll do this as a homework problem, sir. It's a very nice question. We will actually compute what is the overhead in terms of carrier cyclic prefix, and from that you will understand why you want to keep the cyclic prefix. Why do you want to keep delta F to be smaller?
So,
okay.
So you are saying that if we use higher subcarrier spacing when frequency band is in say millimeter wave, then since symbol duration will be less, and that symbol duration will be eaten up by the your cyclic prefix, right?
Yes. So your cyclic prefix, the cyclic prefix overhead will be higher. Yeah, and you don't want to do that because it's waste of resources. Yeah, that's the reason why you want to keep it delta F to be smaller. Okay, but in millimeter wave systems, you don't have any other choice because mainly phase noise. And another thing is, of course, latency. It's a question of latency also, how much latency you want in the system. So it's a trade-off between all these three things. And based on the trade-off, they made this choice.
Sir, could you please explain what is FR1 and FR2? I just...
Okay, sorry. FR1 is called the frequency range 1. So frequency range 1 is from 0 to 6 gigahertz. Okay. Frequency range 2 is the millimeter wave systems. FR2, it's called the frequency range 2. So that mainly deals above plus 22 gigahertz. Okay, I'll show you the document. So essentially, FR2 is the millimeter wave, FR1 is the sub 6 gigahertz. Okay, is it clear, Chitranjan?
Yes, sir.
Okay. Okay. So the next thing is, so if you look at this document, it says that the subcarrier spacing and cyclic prefix come from higher layer parameters. So they always say where do these come from? Okay. So how do I find out where these come from? So I just select this text and then go to 38.331. 38.331 is the research RRC parameters. If you do subcarrier spacing, there is something. 1 minute. Okay, there's something called IE called bandwidth part. Will come down to. I just want to introduce. So I'll just zoom in. Sorry, please. Okay. If you don't see that, please inform me. So it says that the subcarrier spacing comes from here. So this is called an IE, information element, bandwidth part, information element. Okay. So these come from higher layers. So this is what tells the system what is the subcarrier spacing it should use and what is the cyclic prefix it should use. Okay. So subcarrier spacing is of the type subcarrier spacing. Okay, so essentially you can specify new. There will be one more subcarrier spacing somewhere. Okay, I just saw that. Okay, so subcarrier spacing can be 15 kilohertz, 30 kilohertz, 60, 120, 240, and there are 3 more spare ones. Okay, for higher order subcarrier spacing if required as anyhow. Okay, understood? So this is how the IEs look. I will understand this IEs in great detail. I just wanted to show you one IE now. And the cyclic prefix is enumerated. Enumerated means you can put 2-3 options. In this, the only, if you don't put anything, it's normal, otherwise it's extended. So they give an explanation here. Okay, indicates whether to use extended cyclic prefix or not. If not set, the UE uses the normal cyclic prefix. Normal cyclic prefix is supported for all subcarrier spacing. Extended cyclic prefix is only supported for 60 kilohertz subcarrier spacing. Okay, do you understand how to look at this particular thing? So if you have any higher layer parameter, you just go and search it. 38.331. Fine. Any other questions before we proceed? So in the slides I make, I also put that IE generally here so that it's easy for us to refer. Okay. Now let us go and look at something called the frame structure. Okay. So again, let's go back to this thing. Let's read this out. So downlink and uplink transmission are organized into frames. Okay. See how they gave it in terms of TC. Always they give it in terms of TC. So in this case, what happens? TF is equal to delta F max into NF by divided by 100 into TC. So TC cancels off with this. TC is nothing but 1 by delta F max into NF. So they cancel. And TF is equal to 1 by 100 seconds, which is 10 milliseconds. Okay. So the frame size is 10 milliseconds duration. Okay. That's what you should understand. That's how you should read this particular thing. Okay. So downlink and uplink transmissions are organized in frames with TF is equal to 10 millisecond duration, each consisting of 10 subframes. So each frame has 10 subframes of 1 millisecond duration. Again, you see how they gave it in terms of TC. Okay, everything is specified in terms of TC. Okay, 1 millisecond duration. Okay, the number of consecutive OFDM symbols per subframe. Okay, so in each subframe there are multiple OFDM symbols, and then is equal to. Let me explain you how to read this equation. So in this specifications, always you should read from down to top. Okay, so it's written as number of symbols per subframe for a given subcarrier spacing for a given mu. See how they put the mu. Okay, so number of symbols per subframe given mu is equal to number of symbols per slot into number of symbols per subframe into number of slots into per subframe for a given mu. Okay, so always remember that the way to read a symbol, if you have a subscript and a superscript, is you always start at the subscript. It says number of symbols per subframe. Fine? Does it make sense? Each frame is divided into two equally half-size frames of 5 subframes each, with half frame 0 consisting of subframe 04 and half frame 1 consisting of subframes 5 and 9. Okay, so I'm just I'll show you pictorially what this is. Okay. So again, as I said, so you have a big frame. You have a big frame which is 10 milliseconds in duration. This 10 millisecond frame has 10 subframes. Yeah, that's what I told. This is what is there. Each frame is identified something by called subframe. Frame number. This is not SFN. It's called SFN. System frame number. Yeah. Okay. And each frame is divided into two halves. The first half of the frame 0 to 4 symbols, and the second half of the frame is 5 to 9 symbols. Always everything starts at 0. Always remember that other thing that happens in 5G. Okay, always the counting always starts with 0 until unless specified. Okay. In a subframe, the slots are numbered as, okay, we did not come to that point. Okay, let's read the spec again. So any questions till now? Okay. So I'm just going through this in just detail because for the 1-2 classes I will do this so that we understand how to read the spec, and then I will not do it in such great detail every time. Okay. So then they give an example of downlink frame and uplink frame. Okay. I will tell you when we do the TED, I will tell you what is this timing advance and timing advance offset. Okay. But again, you see everything is specified in terms of TC. It's always specified in terms of TC. That's what you should. Okay. Next comes the slot. For a given subcarrier spacing mu, slots are numbered from 0 to number of slots per subframe. Okay. Remember, subframe is 1 millisecond. In increasing order within a subframe, and NSF. NSF is the slots are also numbered in a frame, also in a frame given by NSF. Slots in a frame and slots in a subframe. Okay. There are n symbol per slot, consecutive OFDM symbols in a slot, where n symbol per slot depends on the cyclic prefix as given in table 4.321 and 4.322. Okay, so it turns out for all subcarrier spacing, each slot has only 14 OFDM symbols. Always there are 14 OFDM symbols per slot. Okay, and let's look at number of slots per subframe. So remember, a subframe is 1 millisecond. Yeah, 1 millisecond. So if you have 15 kilohertz subcarrier spacing, the number of slots per subframe is 1. Whereas if you have 30 kilohertz subcarrier spacing, the number of slots per subframe is 2. When you have 60 kilohertz, the number of slots per subframe is 4. This makes sense, na? As the subcarrier spacing is increasing, the duration of the OFDM symbol is decreasing, and that's decreasing proportionally. Okay. So when you go from 1 to 2, you're going from 30 to 60, the number of slots in a subframe will increase because the number of symbols per slot is fixed. Okay, does this make sense? Okay, so let's look at this in a picture once. Okay, so when you have 15 kilohertz, one slot which is always 14 OFDM symbols takes 1 millisecond. Okay, when you have 30 kilohertz, the same 14 OFDM symbols will be half of the size. So one slot will take 0.5 milliseconds. When you go to 120 kilohertz, it will become 1/4 of 0.5 milliseconds, which is 0.125 milliseconds. Does it make sense? Okay. So with 15 kilohertz, there is one slot per subframe. With there's 30 kilohertz, there's 2 slots per subframe. And with 120 kilohertz, there is 8 slots per subframe. Any questions before I proceed?
Sir, here the fixed quantities are frame, subframe, time, and 14 OFDM symbols per each slot.
Yes, that's the fixed. Correct. You are absolutely right. Okay. So frame is 10 milliseconds, subframe is 1 milliseconds, and there are 14 OFDM symbols per slot. Okay, those are the fixed quantities.
And sir, what is 14 OFDM? 14 number signifies what?
So in a slot, one slot has 14 OFDM symbols, sir.
14 OFDM.
That comes from LTE actually. In LTE also it's like that. So that's come from LTE. So 14 OFDM symbols. We'll understand how this becomes 0.5 milliseconds and other things in a little while. But slot always has 14 OFDM symbols. Okay. It turns out a slot, I mean, except for in EMBB and in broadband and other things, except URLLC, slot is a fundamental unit for scheduling. Because slot is something that we see more and more often as progresses. Okay. We won't generally talk about subframes and other things. I mean, there will be little, but slot is more fundamental.
Sir, in case latency of the 30 kilohertz subcarrier frequency, latency will be around 0.5 millisecond?
0.5 millisecond is a slot. Yeah. I mean, generally what happens is you have to wait for the entire slot before you decode. I mean, not required,
Yes.
but some part of the slot you have to wait. Depending upon
but
signals are there.
Jitendra, as far as URLLC would be concerned, so it doesn't wait for the symbol, but slot, but
You can do it
even at you can do it before start of symbol itself. I mean slot itself.
Yeah, there's something called mini slot that was introduced, but it was never, ratified in 3GPP. Anyway, we will at some point we'll look at that. Okay.
So I think release 16. So that is there, sir.
Release 16, huh?
So when they talked about dynamic spectrum sharing, no, so at that point of time, that is also used, right? Because of the limitation of dynamic spectrum sharing because of CRS and also they have introduced that concept so that data can start at any point of time without waiting for the next symbol.
Next slot, you mean?
Yeah, you're right. Yes.
Next slot. Yeah. I have to look at that once. Dynamic spectrum sharing. Okay, let me just note down. Okay, number of slots. So this is what we finished, and so this picture, I'm just going to zoom it a bit. That gives a nice representation. See, 15 kilohertz has a larger OFDM symbol. Don't worry about the numbers 288, 4096 and all that. We'll come to that later. Okay. You can see that as the subcarrier spacing is increasing, the size of the OFDM symbol decreases in terms of time. Okay. So they all fit in nicely in 0.5 millisecond boundary. Always. Okay. We'll do the computation anyway. Okay. This is what yeah. So this is what anyway. So I discuss it. Just have it one reading, and then we'll go ahead. but they are not implemented. The mini slots are not implemented in release 15. I don't think they are implemented in release 16, but I'll find out once. Okay, let me just find it out once. Okay. Please stop me. Pankaj said, sir, 14 OFDM symbols means.
So in earlier slide, you said 7 symbols per slot. Is that a case in 5G?
No. That's why I put them in red. They are not implemented. When they started 5G, they wanted to do all this, but they are not implemented. That's why I put them in red and say not implemented in 5G. Release 15. Okay.
Right.
So release 15 and 16 only supports 14 symbols.
Yes.
Okay. Tell me, sir, please.
Yeah, that's why they use actually 2 slots of 4G when they do dynamic spectrum sharing. Yeah.
That
so
is
that 14 symbols becomes equal. Yeah.
Yeah, exactly. In LTE, it is 7 symbols and subcarriers. So Pankaj said 14 OFDM symbol means 14 into n subcarriers. Yes. So when I say OFDM symbol, I mean the OFDM symbol in time. Essentially, the entire 14. I mean all the subcarriers after you take IF50. Okay. If you have 4096 IF50, you will have 4096 symbol. I mean samples. And those consider one OFDM symbol. Okay, so when you have 14 symbols, 14 into n subcarriers. Not subcarriers. This is why you should not put subcarriers. That's the only issue there, Pankaj. Okay, so this I have to introduce ports, but I'm not going to introduce ports right now. I'm just going to give a high-level definition of ports because we require to go ahead. I'll teach ports in great detail when we do MIMO in a few more classes. Okay, so for now, what we should assume is what is a port. You can think of a port as an antenna, okay, but it's not correct. Okay, it's not exactly an antenna, but for now, for whatever discussion we're going to have, you can think of a port as equal to one antenna. Each port is equal to one antenna. Okay, and the basic definition is each port will have its own reference signals. Just for the next few classes, let's assume this. This is not entirely true, but it's good enough to start. We'll assume that port is equal to an antenna. So if you have 4 ports, it means you have 4 antennas. Fine. That's what we'll assume for now. And when I teach MIMO, I'll exactly tell you what the port definition is. It's a little bit confusing. I don't want to get into that right now. Next comes the notion of a resource grid. Okay. So there's some more material here. This is mostly about something I'll teach when I do TED. Okay, when I do TED, I teach this part. Okay. Okay. Again, antenna ports also I'll teach in great detail when we do the MIMO. For now, let's assume an antenna port is nothing but an antenna. Let's go to the resource grid. Okay. For each numerology and a carrier, a resource grid of n grid size into number of subcarriers per resource block subcarriers and number of symbols per subframe OFDM symbols is defined. So what they are saying is, okay, this is I just summarized this. Okay, so they define a resource grid like this. Okay, so there's a grid size. I'll tell you what the grid size is and number of subcarriers per resource block. Okay, I didn't tell you what a resource block is, but the grid is defined. I mean, what you say is divided into resource blocks, and the number of resource block is denoted by grid size. Okay, and the number of OFDM symbols in a subframe forms a time axis. Okay, so just to plot it, so what they are saying is, so we saw resource grid. So here they are saying is number of symbols per subframe. Here they are writing it as number of resource blocks into number of subcarriers per resource blocks. Okay, so this is the time frequency grid. So they're defining the grid definition. This is what they are doing. Okay. Okay. So where are these parameters again? Okay, so these parameters are something in called SCS specific subcarrier. What it turns out is, okay, so the size of the grid and other things depends on the particular frequency that we use. Okay, that's what we will look at now. So is this clear? Essentially, they're trying to define a grid of a certain size. That's what they're trying to do here. Okay, and sometimes they specify uplink, sometimes they specify downlink. If not, if it's clear by context, they just drop this X. There's an X here, na? I don't know if you can see this X. Okay, this X, they keep it or drop it depending upon the context. Okay, I mean, sometimes it's confusing, sometimes it's not. It's very clear on what to do. Okay, okay, so this grid size for a particular subconfiguration U is given by the higher layer parameter carrier bandwidth in a particular IE called the subcarrier spacing specific carrier IE. Okay, so that is what I wrote. What is the subcarrier spacing IE? This IE has something. It has something called the offset to the carrier. It has also the subcarrier spacing and the carrier bandwidth. Okay, so the carrier bandwidth essentially tells you it's an integer from 1 to maximum number of physical resource blocks. Okay, what is a physical resource block? I'll tell you in a minute. There can be at most 275 physical resource blocks. Okay, so that's what this IE specified. And for every base station, you configure this. Every carrier, you configure this. Okay, you tell that the carrier bandwidth is this in terms of physical resource blocks. That will become your y-axis of your grid. That into number of subcarriers per resource block, which is 12, will become the size of your grid on the frequency axis. On the x-axis, it's number of symbols per subframe. Okay, so number of symbols per subframe depends on the mu. For example, if it's 15 kilohertz, number of symbols per subframe will be 14. When it is 30 kilohertz, number of symbols per subframe will be 30. Okay, so on and so forth. Okay. Okay, so this is what it is. Okay, so this is called a resource. So essentially, the finest element is called the resource element, and 12 blocks, 12 subcarriers form something called the resource block. When we talk about the resource blocks here, 12 subcarriers form a resource block. Okay, they always specify in terms of resource blocks, PRBs. Okay, so 12 subcarriers form a resource block. But the fundamental element is a resource element that is exactly equal to your subcarrier spacing. Okay, and how they do the coordinate system is they always give k, l, p, mu. Okay, p stands for the port number. So each port has its own resource grid. Always remember, each port has its own resource grid. Mu is the subcarrier spacing. K always denotes the y-axis, the frequency axis. L always denotes the time axis, the OFDM symbol number. So 3, 2, for example, implies the third subcarrier in the second OFDM symbol. The third, so it starts from 0, na? 0, 1, 2, 3, 0, 1, 2. So this element where my, sorry, this element where my cursor is a 3, 2. Okay. So K, L is, K is always the subcarrier, L is always the OFDM symbol. Okay. So the element in a, so that is that's the coordinate. The element inside that is always defined as A, K, L, P, mu. Okay, this is a notation. We should remember this notation. Is this clear?
Sir, just now you said that L is the time domain. Now you are saying it is the OFDM symbol.
K, no, K is always the frequency domain, sir. K.
Sorry, L. I'm talking about L. You have said that it is the time domain.
L is the time domain. So time domain means number of OFDM symbol. OFDM symbol 1 is the first thing. OFDM symbol 2, this axis.
Okay.
So L is equal to 0 is this, L equal to 1 is this, L equal to 2 is this. Remember, the interpretation of the frequency grid is this whole thing will come as one OFDM symbol. Okay, so this will have some, it will take some time. This is the second OFDM symbol, third OFDM symbol, fourth, fifth, sixth, so on.
Okay.
Is this okay, sir?
So basically, K means subcarrier number and L means symbol number.
Symbol
so
number,
that,
exactly.
That will tell you the particular resource element.
Resource element in the grid. Yeah, exactly. And you should always remember.
So can we consider this one grid is for a particular beam? As you said, for the port, can we also consider that as a beam?
Some vague sense, yes, sir. But for now, let's just think as an antenna. Okay, it's easier. Until once I come to MIMO, I'll tell you what is a port. So each port will have one grid. Okay.
Okay.
Sir.
Mr. Kamal, please.
Sir, please repeat P and mu. What are these?
P is the port number. Okay, so what I'm trying to say is, let me show you my screen. Okay, suppose you, this is again, I'll confirm what is port later, but for now we can think is you have two antennas. Okay, so this will have one resource grid, this will have another resource grid. Okay, so you understand what a resource grid is now. Now OFDM resource grid, we have done that enough. Okay, so alpha k comma l p comma mu. Mu is the subcarrier spacing. Anyway, generally we fix mu. Okay, but that they just specify that so that it's easy. Mu is the subcarrier spacing. Okay, so essentially it can be 0 kilohertz, 15 kilohertz, 30 kilohertz, something. Mu will become 0, 1, 2, 3, 4. P is the port, so this is port 1. Okay, so essentially this will be alpha 1 comma, if you are using 30 kilohertz subcarrier spacing, 2, sorry, 1 comma 1, k comma l. Okay, k comma l will be some position here. Okay, maybe some position here. Okay, similarly alpha 2 comma 1, k comma l will be a position here in this antenna. Okay, position on the value there. Position is k comma l and the value there is that. Okay, is this clear?
Yes, sir. Clear. Clear, sir.
Okay, thanks.
Sir, in the previous slide, in this slide, that ANSC RB is there, na? You said we should read it from bottom to top. Then how it is written, sir? Number of RB per subcarrier it is written, na?
Number of subcarriers per resource block. So this is called resource block. 12 elements make a resource block. So number of subcarriers per resource block is 12. Okay, this is not the time axis. This is not the time axis. I just put it here. I should have put it somewhere here. Yeah. I just put it there so that it's easy. Nothing more than that. Yeah. So 12 resource. Chitranjan, tell me please. Sorry. So 12 subcarriers or 12 resource element makes a resource block. So what is a resource element? Resource element is nothing but one subcarrier times one OFDM symbol. In one OFDM symbol, if you take one subcarrier, that's called a resource element. That's the most fundamental unit in terms of the resource grid. 12 of this 12 consecutive resource elements in the frequency domain makes one resource block. Okay? A resource block is a contiguous set of 12 subcarriers. Okay? And what happens? So essentially, you specify the grid in terms of resource, resource elements. Resource elements on the y-axis and OFDM symbols on the x-axis. Is this fine? Chitanjan, does it clear your doubt?
Yes, sir.
Okay. Yes, sir. Okay. So the next question is.
Sir, one question, sir. That one OFDM symbol will have 13 subcarriers. Just in previous slide, you can go, sir.
Yes, sir.
It is having 13 symbols that a resource element in one OFDM.
Can you repeat, sir? Your voice was a little bit breaking for me, please.
Sir, in one OFDM symbol, it will contain 13 resource elements.
No. OFDM symbol elements is different, sir. 1 minute. That's just me. Let me show you my screen. I think let's just. Maybe the resource grid. Where did we do the resource grid? Yeah. You remember this time frequency grid, sir?
Yes.
So the x-axis was the symbols. Okay, y-axis was the frequency. Okay, so one symbol here, one symbol means this whole thing. When you take the IFFT and put it, that becomes one symbol. Okay, so
it can take how much that unit of that grid? It can vary, or it can have the fixed one.
Which one, sir?
That in time axis that it will go on the frequency axis.
Can I answer you, sir?
Yes, Ashokji.
So basically it will depend upon what is the bandwidth you have. If suppose you have 50 megahertz of bandwidth, so if you divide the, and you're using say subcarrier spacing of 15 kilohertz, so if you divide 15 megahertz by 15 kilohertz, you'll get around 3000 subcarriers, right?
I
So
will tell you.
yeah, so 3000 subcarriers with one symbol duration, so that much will be used for that symbol duration,
Okay,
if that answers your questions.
Pandey sir, I now understood. So essentially, you're saying how much can be the y-axis length?
Yes. How much you can have in y-axis?
That is what this slide answers. It depends on your bandwidth and your subcarrier spacing. Okay. So let's just go to the slide in detail. So a resource block is a contiguous cells of 12 subcarriers. Okay. So each numerology has a limit on the number of physical resource blocks it can support. Okay. So that is specified in 38101 and 38101 Okay. So for example, this is something I copied from 38101. It tells you what is the maximum size or in terms of resource blocks that can be there for different bandwidths for different subcarriers. So for example, let's take a 15 kilohertz. This table says 15 kilohertz can support up to 50 megahertz. And for 50 megahertz, you have 270 resource blocks. Okay. So 270 resource blocks means 270 resource block, and each resource block has 12 subcarriers. So you can support 3240 subcarriers will be there. Okay. So the y-axis maximum thing for 50 megahertz is 15 kilohertz is to 3240. Okay. So this specifies the maximum, but the actual thing you can set it anything you want, and that is what exactly is specified by this IE, carrier bandwidth. Okay. So if devotee gives only 15 megahertz, okay, that is not, so then, okay, so 15 megahertz means essentially it says that maximum you can use 79, but you can also do little lesser than that. I mean, lesser than that also if you want to. Okay, this is a maximum transmission bandwidth. So suppose you give only 14 megahertz and not 15, then what do they use is they take 15 and then you can reduce this number of RBs as and how you want. Okay, and that you specify that in terms of carrier bandwidth, in terms of resource blocks. Pandey sir, this answers this question?
Yes, sir.
Okay. So this table is very important in that sense that you can see that now 15 kilohertz only supports up to 50 megahertz. After that, there's no support for it. Okay. 30 kilohertz supports everything, and 60 kilohertz, for example, does not support 5 megahertz. It supports the higher thing.
So is there any reason for that, or it has been from the experiment?
So it's not an experiment. So what they felt was if you have lower bandwidths and other things, you can use smaller subcarrier spacing. Smaller subcarrier spacing. Higher subcarrier spacing is for anywhere millimeter waves which have larger bandwidths. Okay. So the millimeter wave table also I put here. You can see this. Millimeter wave support is from 50 megahertz. Okay, 60 kilohertz and other things don't support below this thing.
Yeah, for two. Yeah. So why that do not support? Is there any logic behind, or it has been somehow?
I don't think there's any logic behind the law. It's not.
Or is it maybe due to FFT complexity?
It is due to the size of FFT, requirement of the FFT. I think Vikira this side. That is the limitation. IFFT or FFT.
We can do lower FFT also, but that's one thing. But mostly, what the idea was
practical IFFT design of practical IFT or FFT limits that I know, but how I can't explain. But
I will tell you that. In the next coming slides, that is there. But see, the main intuition was that higher subcarrier spacing will be used for higher bandwidths. And higher bandwidths you will generally have higher frequencies, and higher frequencies have larger bandwidths. Okay, that was the intuition. That was what the guiding principle was. But what as Mr. Roy said was also correct. There are some limitations in terms of FFT sizes. We will do that computation. Well, I'll tell you exactly when you say if you have 270 subcarriers, how do you do your FFT sizes and other things. Okay. Okay, so let's look at something. I want to emphasize this a little bit. By the way, So this is the maximum number of subcarriers you can use for a given frequency. The absolute maximum is 275. Okay, for in the 275 is also not allowed to be used. Only 273 is allowed to be used. Okay, that's the maximum that you can get. I think 275 is not there anywhere. Yeah, 273 is the maximum you can use, but 275 is allowed. But the RF specification prevents it to go, only allows till 273. Okay, the baseband specification allows it to go to up to 275 resource blocks. Okay, so if you take 100 megahertz bandwidth and 30 kilohertz subcarrier spacing, you are using 273 subcarriers. So if you are using 273 subcarriers at 30 kilohertz, the effective bandwidth you are using is 98.2 megahertz. So this implies you are 98.2% efficient because in a 100 megahertz bandwidth, you are using 98.2%, 98.2 megahertz. Compare this to LTE. LTE for 20 megahertz, approximately 18 megahertz is used, and you have 1 megahertz, guard band on both sides. Okay, that is 90%. So efficiency, I mean, they also wanted to increase the efficiency of 5G in terms of spectrum. That's the reason why they allowed more PRBs to be used in 5G NR. Fine? Does that make sense?
Yes, sir. Yes.
Okay. So you can compute the efficiencies for each of this, but I'm not going to do that. Okay. It's already 10:54. What I'm going to do is tomorrow, I'm going to continue with the slides. I'm going to talk about FFT size sampling, and we are going to answer this question that we have today. What is the FFT size that you can do for each of this? That will continue in the next class. Okay. So what I would suggest is, I would suggest you to take this spec and read it till at least what we have done, so that you get used to it. Nothing more than that. It's just if you read it once, you'll get used to it. Fine. So I'm going to stop now. Thanks everyone. So I'm going to see you in the next class. Okay. Thank you.